Shall we go? Okay. Hello, I'm Luciano Raso from TU Delft, and I'm presenting this poster about dynamic modeling of predictive uncertainty by regression absolute error. With the same title, there's a recent publication on water resource research, and it's work I've done with Francesca Pianosi, who works at Politecnico di Milano. And it's about estimating the variance, basically to build up a distribution around a point estimation of a deterministic model. So what happens nowadays that you have typically you have a deterministic model, but you want to know the entire distribution around that point because of, in this case, was a reservoir management. And the problem is that in hydrology, typically the hypothesis of the error, which is independence, and the fact that errors are identically distributed, those hypotheses don't hold. And it's a problem. But as we've found a way to solve it, at least the first two problems. The first one, independence, is relatively easy to solve because basically you can build up a linear regression on the previous errors, and then to widening the error. So still you have the problem of heteroscedasticity, so the fact that the variance changes in time. Now, for people who know the arch model, basically you estimate the variance with a regression of the squared error. What we do here is a similar approach, so we build a dynamic model, but it's based on absolute errors and not on the squared errors. Why? Because it's much easier to estimate a time series built on absolute errors. And the effectiveness of this method can be shown on the applications, in which we compare the Dumbre model. It's called Dumbre. Sounds like Dumbre, but it's in fact actually this resembles the fact that it's a simple model. I mean, not completely stupid, but still relatively easy to apply. So if I show some results in this plot, we apply to two test cases. One in Switzerland, Rhone River, and one is in Lake Maggiore. Here we have the hydrogram, and here we have the error in time, and four different models to which we compare the Dumbre model. Now, if you look at the likelihood, log likelihood as an estimation of the quality of the goodness of the estimation, we see that the Dumbre scores much better, both in calibration and validation, than all the other models. And compared also to the two mixed model, which is a work previously done by Bettina Scheffli, and also to the Lake Maggiore, we see that basically it's very interesting. For example, this point here, if you can zoom, it can be interesting, in which if you look at the receding part of the curve, let's focus on this case. We linked the variance to the precipitation. In fact, actually, the uncertainty is much higher after precipitation event. But in the receding part of the curve, it's much easier to predict the uncertainty. The uncertainty is much lower, much smaller. In fact, if you look here, you see the state-dependent model in which the variance changes linearly with the flow. You see that the estimate is too large. It's much wider than necessary. And our model, the Dumbre model, actually estimates correctly, so moves in the right way. And so to conclude, we can say that this model, the Dumbre method, it's effective in the case you want to you have a deterministic model and you want to build up a distribution around it. So it's a very applicative because it's separate from the modeling of the hydrological process in itself. So in the poster you have a link to the paper on water resource research, in which we show all the details of the work. Thanks for your attention.